All right, all right, all right. Advanced Math 8, here we go. We got lesson 4.1.4, day 2. All right, so the last time that we were here, we were looking at the El Toro basketball team. So you were doing this, and you guys were supposed to come up with your own lease or your own line of best fit. And in class, hopefully we noticed that all of our lines were different. They weren't the same. We have a little bit of a problem there. So what we want to do today is figure out what the very best line would be for it. So I've got my line that I've got. You got your line. We all have different lines, and that's going to be okay. We're going to figure out how we can come up with a line that we can all agree is the best line. Now, you guys had some discussion questions, and here's what you should have kind of come to a conclusion of. The very best line will be the line that has the least amount of residuals, because residuals is how far away you are from the line of best fit. So if you can get a line where most of the points are as close as possible to that line, that's going to be the best line. And we call that a least squares regression line. So in order to do that, what we're going to do is we're going to find out what our y-hat is. So we're going to look at our line of best fit that we came up with, and we're going to write down our predicted values. Then we're going to look at our residuals. Now we have a problem with our residuals though. Our residuals are positive and negative numbers. So if I've got positive and negative numbers, I really don't want to think about them as positive, negative, because I just want to see how far away they are from that line. So I don't want one positive number canceling out a negative number, because that's not really how far away. So we can think of it in terms of absolute value, but statisticians, instead of looking at it in terms of absolute value, they look at it as in terms of squaring, because squaring also, like absolute value, will always make numbers positive. So if you have a positive number and you square it, it's going to be positive, and if you have a negative number and you square it, it's going to be positive as well. So what we're going to do is we're going to take your data, figure out its predicted amounts, find out the residual, which is y1 minus y hat, and then we're going to square those residuals. So the line that is the absolute best will give us our smallest sum of our residuals, because that'll mean that, of all the different residuals that they had, whichever one has the smallest sum is the ones where the residuals are the closest to the actual line. Now, this could be a lot of work, especially if you have a calculator that doesn't do all this work for you. So what we're going to do is I've made a Google Sheets that we can actually work with. So it should be in your Google Classroom. And it's easy enough to make. I'll show you how to make it. But here's my Google Sheets that I've made. So I've already put in, okay, so over here, these are all of our players. Here's their time played. Remember, that's X1. Here's our actual our actual points. So that's our Y1. And then we're going to find our predicted amounts. Now, what I've done here is I've created up here, you can see it says B2 times B17 plus B18. So basically what I'm going to do is B2, that's our X value, and then I'm going to multiply it by the slope and then add the y-intercept. So all you need to do at this point is enter in your slope and your y-intercept, and it's going to calculate everything for you, because I'm a nice guy. So for me personally, looking back at this line of best fit, personally what I've got is, okay, I worked it out. I picked these 2 points to make a line of best fit from, and I got a slope of 0.3485, and let's see, and I rounded it. I made it 0.35, and then I ended up with a negative y-intercept of negative 8.75. So those are my 2 numbers that I'm going to work from. I'm going to use 0.35 and negative 8.75. So that's my slope and my y-intercept. So going back to my Google Sheets that I've made, all I have to do now is plug in 0.35 as my slope, and then go down here, and my y-intercept was negative 8.75. 7.5. That's a 7. There you go. And now it's done everything for me. Hooray! I have my predicted values all down here. So these cells right here, I've just written the equation that this one times the slope plus the y-intercept gives us our predicted values. And then this cell right here just says, okay, take this value, the y1, and subtract the y hat, because that's how you find residuals, right? You just take the actual data minus the predicted data, and that gives you the residual. And then this last one just says to take this number and square it. And then finally down here, this is the sum of my squares. So if you square all of my residuals, so remember that Scotty Sorton, he was like really far off of everybody else. So he's got a big residual, and when you square it, you get a really big number too. So my sum of my squares is 2,422,851. So what you guys should do is take your data and plug all that data in, and then you can fill out your worksheet up on top. So I'm going to go ahead and pause for a second, and I'm going to fill out my worksheet here based on that Google Sheets that I just did. So let's pause for a second, and let's fill in all of our data. All right, so at this point, I've got all my stuff down. I got my predicted. I got my residuals, which is taking the y1 minus y hat, and then I square it. And if you look at it, you might say, wait a second, your numbers are broken here. -2 squared is 4, not 3. Well, inside of, if you're using like something like a spreadsheet like I did, these numbers are all rounded. Like I made them round to the nearest whole number. So this number is not actually -2, it's -1 point something, you know, and then that's why this is 3, is because it's rounding all the numbers for me. But when it's squaring it, it's not squaring the rounded number, it's squaring the actual number. So that's why some of these numbers don't look like they're squares. It's because these numbers inside of the program, inside of the spreadsheet, they're actually a different number. It's just rounding them all for right now. So these are all working. Tested it out, so I know that it's pretty close. So anyways, I get a residual squared of 2,422,851. So check out yours. Did you get a smaller residual for your sum of your residuals? Was yours smaller or was it bigger? The residual that was the smallest sum is the best line that we've come up with. Okay, so if we can find a residual of all the different ones that all the different people in all our different classes made for their line of best fit, that would be the better line of best fit compared to another one. So if you came up with a residual that was only 1 million instead of my 2 million, your line's better than my line. Okay, so we've got a whole bunch of different lines, and hopefully in class you guys compared it to different lines and saw what was going on. But now we need to find out what the absolute best line is. And this is what we call a least square regression line. And sometimes we just call it a LSRL, least squares regression line. So this is a mathematical formula. There is an actual formula where we could hand do this, but it takes a while. So we're going to make Desmos do it for us. So our next thing that we're going to do is we're going to pull out Desmos. So here's Desmos. So don't go to student.desmos.com, just go to desmos.com and then choose their graphing calculator. All right, so what we're going to do is we're going to choose this plus item that says add item, and we're going to add a table. Now here the table is x1, y1, just like I've been doing in all my notes, see? See where that comes from? Okay, so now I need to add in or put in all of our data. So let's see, the first one is 3093, next one's 2825, then 1886, then 1641, then 1919, then 2088, then 1065, then 7, then 740, then 685, then 274, 545, 671, 191. Now you really want to make sure that this is exactly correct. You want to go back and double check your X's to make sure that all of your X1s are right. 3093, 2825, 1886, 1641, 1919, 2088, 1065, 7, 740, 685, 274, 545, 671, 191. All right, so I've got all my X's correct, so now I'm going to put in my Y's. 2491, 1496, 594, 564, 688, 351, 376, 5, 278, 216, 98, 182, 185, and 36. All right, so let me double check my Y values, make sure I plugged it in right. 2491, 1496, 594, 564, 688, 351, 376, 5, 278, 216, 98, 182, 185, 36. All right, awesome. All of this is working out so far. So again, what we're doing is there's a mathematical formula that we can actually do to find the least squares regression line. But remember, in this unit, it's not really about can you find it or can you calculate the least squares regression line or the lines of best fit or whatever. The calculations aren't really a big part of this. What we want to focus on is looking at the data and being able to interpret the data. So that's why we're kind of cheating here and letting Desmos do all the work for us. So the next thing that you're going to want to do is go to a new enter spot here. So now I'm on spot 2. And now I'm going to tell Desmos that I want them to find the perfect line for my data. Now you'll notice over here, oh, my data is not really showing up. It's because it's so spread out. So we probably need to spread out our data so we can see all of our stuff. So I'm going to zoom out a little bit. Oh, okay, that's better. All right, now I can see all my data there. Yeah, I liked it better right there. Okay, so there's all my data. I've zoomed out. It looks like the scatter plot that we saw at the beginning of the problem. So what I'm going to tell Desmos is, hey, I want you to make a line that's a line of best fit that goes through this one. So I'm going to tell the problem, I want it to make a linear equation. So that's y equals mx plus b, right? Well, so my y's up here are y1. So I'm going to say y1. Instead of equals mx plus b, there is no equal for this one because these points are not in a straight line. So I want it to approximate. And what we do is use the tilde symbol. This is the tilde symbol. It's right next to the 1 symbol on your keyboard. So I want y1 to approximately be mx, and we want to use these x values here. So I'm going to say x1 plus b. And now we have a line of best fit. So here's my line of best fit. Let me get over here. Oh, okay, so I'm over here now. So it has calculated out for me a beautiful line of best fit here. They tell me that my slope should be 0.594619 and that my y-intercept should be negative 208.795. And that is the very best line of fit. So we're going to go ahead and go back to our worksheet. So I'm just going to keep this over on the side for right now. So we're going to go back to our worksheet. It says write the equation of the least squares regression line. Okay, so our predicted value is going to be, and I'm going to keep it down to 4 decimal places. So I've got 0.5946. That's my slope according to Desmos, X, and then minus 208.795. And this is what the calculator is telling us is the very best line of fit. This line of fit would minimize our residual squared. So it would have definitely a residual that's less than my 2,422,851. It would have a much smaller residual than that. In order to prove that, let's go back to our Google Sheets thingamajigger. Where was that at? Here it is. So let's look at Google Sheets over here. Okay, let's change the slope to my new regression, my least squares regression line. So that's 0.5946. There's my slope. My y-intercept is negative 208.795. And so the smallest possible sum of the squares would be 1.5 million. And notice, remember mine was 2.4 million. So this is much less. So what we want to do is minimize our distance from the line of best fit. And so this equation right here with a slope of 0.5946 and a y-intercept of negative 208.795, this will give us the very best line to minimize our residuals. Now you'll see how they did it. They got really close to Scotty Sorden compared to my line. So my line kind of left out Scotty Sorden and I had a huge residual right there. This one kind of kept the residual a little bit closer. So there you go. There's our line of best fit. And it gives us a least squares of 1.5 billion. All right, so let's go back and fill out some of the stuff. Sketch the LSRL on the graph. So this is the graph that we were doing the other day. So I'm not going to do it right now, but you can kind of sketch it. You can look at Desmos and kind of figure out where it would be. It was a much steeper line than what I had here. Okay, so if you look at Desmos, their line, super steep compared to my line. Okay, so we can sketch that, do that on your own time. What's the sum of the squares of the LSRL? And we just plugged that into the Google Sheets, and we got 1,502,806. Was it smaller than mine? Yes. And that's the whole point, is this is a better line than mine because it minimized the residual by looking at the squares of the residual. So was it better? Was it smaller than yours? Yes, it's smaller. It had to be smaller. Now, how many points does the LSRL predict for Antonio Cusick? Okay, so I would plug that in. I'd say my prediction for Antonio is going to be 0.5946 times 2,103 minutes and minus 208.795. All right, 28. So if I plug it into my calculator, I do 0.5946 times 2,103 equals, I get 1,250 point blah, blah, blah. And then I'm going to subtract 208. Isn't this fun just to watch me do calculator work? 0.795. So here I get 1,041.6488. Since this is talking about points, I'm going to round to the nearest point. So that'd be 1,042. And if you go back to your previous notes, you notice that this is pretty different. All right, interpret the slope and the y-intercept. So the slope for this one is saying that, remember, we're comparing the time played to the total points. So my total points are going to increase since this is a positive slope. My points will increase by 0.5946 points. For every X, which is time played. So for every minute played. And we have to ask ourselves, does that make sense? Yeah, it makes sense. The more time they play, the more points they'll make. And this says that for every minute they play, this is how many points they're going to make. So a little bit more than half a point per minute that they play, on average. Our y-intercept, though, doesn't make a lot of sense. According to our y-intercept, it says that if they play, because remember the y-intercept is when x is 0, so if they play, time is 0. So if they play 0 minutes, the y-intercept says that they'll have negative 208 points, which is just crazy talk. And this happens quite a bit when we're doing a least squares regression line. The closer you get to the farther away you get from the middle of the data, the less your prediction, the less your model will make sense. So since we're getting pretty close down to the end of our model, it's making less and less sense. So in this case, my least squares regression line kind of comes down here, and what we're going to find out is, for 300 points and below, our model probably doesn't make a lot of sense. And my light just went off because I haven't been moving enough. There you go. So that happens like every day. So anyways, what we're going to see is if we were graphing our model here, we'd see that it crosses over here somewhere around 300. And so we would notice that, for our really low numbers, our model doesn't make a lot of sense because we end up with negative points for minutes played. So our model makes more sense over here, but the farther away we get from the middle of our data, the less our model is going to make sense. And that usually happens when you do a least squares regression line. The farther away you get from the middle of your data, the less your model will make sense. All right, so that's all I have for your notes. Math hard. Goodbye.